So, welcome to the session on coordinate transformations. In this session, we will be using the subscript notation which we have covered in the last two sessions, and we will apply these coordinate transformations to define certain parameters that we will be using in this course transport phenomena, and we will also be using these expressions to derive some of the equations that we will need later on. This coordinate transformations has three components, which is basically relocation of the origin of the coordinate system and the dilation of the unit cell, which is basically either contraction or expansion, and then rotation of the coordinate axis. We will be taking up only the rotation at this juncture. We will look at the other two aspects later on as we will need. So, we will be looking at what are called Cartesian coordinate system, which means basically we are looking at orthogonal coordinate system, and what we mean by orthogonal coordinate system is indicated here. Let us look at, for example, here x, y, z axis defined as x1, x2, x3 with a hat symbol showing that they are the three unit vectors along the three normal directions. What we mean by the normal directions is that when we take a dot product of any unit vector with itself, then we would see that it should be equal to 1, and then whenever we take the dot product with respect to something that is normal to it, then we should get a 0. Okay. So, this is what is defining the orthogonality of the axis. We also have another aspect that is embedded in this particular system, namely the so called right handed system. So, we could choose the coordinate system to be either right handed or left handed. So, what we mean by right handed system is that if we take a cross product of x1 and x2 and then dot that with x3, we should get 1. If we get minus 1, then it would be a left handed system, and the dimension what we get for the triple product x1, x2, x3, this gives us whether the unit cell has been normalized with the three unit vectors being of magnitude 1 or not. So, we can choose these to be different in any other coordinate system, but in Cartesian coordinate system, particularly the orthonormal xyz axis that we are very familiar with, then we are going to use the way we are defined here with the three unit vectors normal to each other. So, by coordinate transformation, as I mentioned earlier, we are only going to look at the rotation. Okay. So, assume that the origin of the coordinate system has not changed and we have only done the rotation. So, ensure that the way we have described the three axes x1, x2, x3, ensure that the handedness has not changed, namely the right handed nature of the coordinate system is preserved. So, this is what we mean by the rotation of the coordinate system. As I have shown in the image, the location of the three unit vectors has now changed. Now, when that changes, how do we then represent the new coordinate system in terms of the old coordinate system and vice versa, and then if there are quantities such as vectors, then how do we represent the components when the coordinate system has changed. So, this is the task that we have ahead for this session. So, the example transformation can be then taken up, and we will do a 2D rotation so that we can derive the expression easily. So, what we do is basically we will rotate the coordinate system about the x3 axis, and we rotate by a certain amount which is basically given by theta angle. So, which I have given here. So, which means that basically the new and the old x3 unit vector is coinciding, but the x1 and x2 are now rotated by a certain angle theta that is given here. So, what we will do is that we will derive how we can represent the unit vectors with respect to the older ones and vice versa. So, what we do is basically we draw a line of unit length about the unit vector which we want to express, and so what we want to do first is write the new unit vectors in terms of the old ones. So, what we do is that let us first write x1 in terms of the older coordinate systems. So, x1 star is the new one. So, this is the new one. So, we take a unit vector here we have shown it here. Okay. So, this length is 1. So, if this length is 1 and the angle it makes with respect to the old x1 axis is theta, then we can see that the components along the x1 and x2 are then given by cos theta and sin theta respectively, which means that we can express x1 star in terms of x1 and x2 as given here. So, similarly we can also express the x2 star, and for that what we do the same way, we take up a unit vector along the x2 star and then take its components along x1 and x2, the old coordinate system, and then we see that when we express that in terms of the old coordinate system, we get this relationship x2 star is equal to minus sin theta x1 plus cos theta x2. We can see that the sin theta and cos theta have changed their position, and then there is a minus sign coming, that is going to be of use later on to see what will happen to the transpose of certain matrices that we will be talking about. So, at this junction we can just write this, and do we need to write x3 star in terms of anything else? So, we see that we do not need to worry, because we know that x3 star is the same as x3, because the rotation is about the x3 axis. So, x3 axis has not changed its orientation at all. So, we can just leave it like that. So, we now have basically the 3 new unit vectors in terms of the 3 old unit vectors. So, we can then connect them and see how those expressions look like. So, that is then given in this form here. So, you could see that these 3 are the equations that we have now come up with. So, x1 star in terms of x1, x2, x3, x2 star in terms of x1, x2, x3, and then x3 star in terms of x1, x2, x3. So, we can now represent these 3 equations, linear equations, in matrix forms. The reason why we are going to do it in matrix form is because we could then give symbols to those matrices and then use the subscript notation to make the same expression in a very brief manner. So, what we do is that we write it in the form of matrix multiplication. So, let me highlight and show you how this looks like. So, x1 is then given by this multiplied by this, that is x1 cos theta plus x2 sin theta plus 0 into x3. So, that is how we are doing. So, this is the typical way matrix multiplication is done in the engineering mathematics courses. So, this must be familiar to us. So, what we now want to do is that we want to then write these expressions with some symbols, so that using the subscripts we know the positions. So, that is what we are going to do now. So, we want to call each of those terms as the elements of a matrix T. So, T11, T12, T13 are then nothing but cos theta, sin theta and 0 respectively. So, we could then write this expression. So, we are now using the short form T, so that we represent that as a matrix. So, this matrix is nothing but the transformation matrix. So, this has a specific name. So, that is basically coordinate transformation matrix. So, this is unique to the kind of rotation that we have done. So, when the rotation angle changes, then the elements of this matrix also will change, and the matrix itself is expanded here. So, when we look at the expression here, so if you notice the expression, so here in this expression if you notice here, so let us just write x1 star, and we write this as T11 x1 plus T12 x2 plus T13 x3. So, you could see that there is a summation that is taking place, and that is about the second index here. So, we could then use the subscript notation to indicate. So, when we have a dummy index in the second position of T, then we can see that we can get the summation implied by the subscript notation itself. So, that is what we are going to do here. So, here basically what we have written here is that we have used the second index as a dummy index matching with that of x, so that it is implying that it is summed up over the I index from 1 to 3, and the first index corresponds to what is the new unit vector that is being expanded. So, in a very brief manner we are able to write the transformation of the unit vectors from old to new using this expression. So, we could also do the reverse. So, when we do the reverse, we have a very interesting observation to make. So, let us go through that exercise now. So, the reverse is as follows. We have to now write the old unit vectors in terms of the new ones. So, what we do is same as what we have done earlier. So, here we have seen that there is a unit vector which we want to expand in terms of the components along the new axis. So, the unit vector is along the x1, the old one, and its components are given by cos theta and sin theta, and we could also see that the expression comes like this. So, x1 in terms of x1 star and x2 star are written here. So, we could again expand the x2 in terms of the two components. So, we do the same thing here. So, we take up the unit vector along x2 and then take its components along x1 star and x2 star, and then we obtain this equation. And the equation for x3 is of course known to us because we have not changed its orientation at all. So, you would write this way. Okay, so, we have now also the old unit vectors in terms of the new ones. So, we could again express these three relationships as a set of three equations and with a matrix form. So, that is what is done here. So, they are expressed here as three equations, and then they are then converted into a matrix form here, and this is the transformation matrix here. So, this is the transformation from the new one to the old one, and we can see that there is one difference with respect to the previous matrix, and that comes at these terms. So, you could see that the minus is now appearing on the first row. Earlier when we are expressing the new unit vectors in terms of the old ones, the minus was appearing here, and in terms of the old unit vectors here we have getting this. So, this is the only difference that we are getting, otherwise the elements are same. We also notice that it is a transpose of the other matrix, and when we want to expand this in terms of the subscript notation, we write it here in this manner. Okay. And you could see that we are able to use the same symbol TPI same as earlier, the reason being that the summation is now over the first index of t, whereas in the earlier case it was over the second index of t. So, by changing the index we are then able to retain the same transformation matrix T. Okay, so, I want to just alert you here about this particular difference, because it is very important that we do not lose out on this particular difference. So, I want to highlight here. You see that when we are expressing the new unit vectors in terms of the old ones or old ones in terms of the new ones, the transformation matrix will come as TPI only, and then the index P is meant for the new coordinate system, the index I is meant for the old coordinate system. However, the way these two are different is evident because the summation is over the second two indices here, but here it is over the first and the index of x star. So, you could see that the way we multiply the two matrices is different. The way we multiply the first one is this way and the second one is this way. So, you could see that that is the difference why we are able to write the same expression, but just swap the indices over which summation is happening and then retain the meaning. Okay. So, this is also coming up because of one particular property of the transformation matrix, namely for the transformation matrix we realize that its inverse is the same as the transpose. So, this property is what allows us to write this, and the reason why this property comes up is because the determinant of the transformation matrix T is unity, it is 1. Okay. Because of that this particular property comes up, and therefore, then we are able to write. So, what we now need to remember is only one expression here. So, whether it is new in terms of the old or old in terms of the new, we have to remember that x star is T times x, and the indices should be such that you keep one index on the left side, one index on the right side, and then put them side by side here below, and then the expression would work for you. And the rest of it basically is the subscript notation, because you know how to expand this once you know the subscript notation. The dummy index is I, so you sum up over the I index. So, that is how you can get the new unit vectors in terms of the old ones or vice versa. Okay. So, there are other ways of defining the transformation matrix T, and I would like to then cover them because different textbooks may adopt different ways of defining them. So, the idea is how do we get the elements of transformation matrix T for any given arbitrary rotation of the coordinate system. So, the way to derive is being illustrated here. So, when it is only one theta about x3 axis, we already know how to do that, but any general case we can just do that here. So, let us look at the transformation which is given in terms of the expression here, okay. And when we expand it, we are getting this expression, okay. So, we take p value to be 1. So, we are looking at the first unit vector of the new coordinate system and expanding it in terms of the 3 unit vectors of the old system. Now, you see I want to get T11 and that is what I want to now check. So, I want to get this. Now, you can see that if you were to pretend x1, x2, x3, the old ones as well as the new ones were to be like variables, then differentiating this expression with respect to this variable will get me only this term out. So, that is what is being done here, okay. A partial differentiation is going to get me that term, okay. So, you could then look at the entire expression in this form, which is very brief. It just shows you that by looking at the differentiation you could get the elements of the transformation matrix in this form. So, the convention is that the first index goes to the numerator and the second index goes to the denominator, and p corresponds to that of the index of the new coordinate system, I corresponds to the index of the old coordinate system. So, if you stick to this kind of a connotation, then we will not make a mistake. So, you could arrive at the elements of the transformation matrix by looking at the differentiation, and this is particularly useful when the transformation is given as a functional form. Then we could use this kind of an expression. We are now taking up the reverse transformation, the old in terms of the new ones, and here you can see from the previous slide we can see that here we have got star on the left hand side, which means that the new ones in terms of the old ones, and here I am writing the old ones in terms of the new ones. So, whichever way we write, we are seeing that we are getting the same expression. So, we can get the same expression, which is very interesting. So, it just shows you that when you want to express the elements of transformation matrix, you take partial differentiation of the old and the new, and the order is not important. The reason why it is happen is the same principle. Basically, the inverse of T is same as the transpose. So, here you can see that the index positions are changed, and what it implies is that we are taking the transpose when you are doing the second way of differentiating, and therefore, the inverse transformation is giving you the same TPI. So, it does not matter now how to remember the expression of T, you just differentiate old in terms of the new coordinate system or the vice versa, and as long as you are able to remember the position of the indices, the first position TPI we write. So, we remember that the first index corresponds to that of the new, second index corresponds to that the old coordinate system, then the expression is going to be correct. So, if we make a swap here, then we will have a transpose of those matrices coming out. So, we should watch out for that. So, an alternate way of defining the elements of T when the unit vectors are given in vectorial form is shown here. So, here what we do is that instead of looking at partial differentiation, we basically look at as a dot products. So, we do the same exercise and we see that we want to get T11 out. Okay, so, what we do is basically we realize that from the orthogonality property of the coordinate system, if we were to dot this with something that will leave behind only this term and not have these two terms, which means that if I were to dot that with x1, then what happens is that the first term will remain, the second, because it is x2 dot x1, it will drop off, third one x3 dot x1, it will drop off. So, I could then imagine that T11 is nothing but a dot product of x1 star and x1, similarly the other terms. So, you could also imagine the elements of the transformation matrix as dot products of the new and the old coordinate system. So, which means that in case the new coordinate system axes are given as a vectorial form of the old coordinate system, then you can just do the dot product and we can get all the 9 elements of the transformation matrix directly using this kind of a relationship. So, either way we need to get the matrix T, so that we can define the transformation completely. Okay, so, there are certain properties of the transformation matrix which are derived from the nature of the coordinate system that is being used here, which is basically the orthogonal coordinate system. So, these properties of transformation matrix are then used to reduce some of the expressions as we derive various quantities later on. So, we know that both the new and the old coordinate systems are orthogonal, and which means that when we dot the new unit vectors, we should get 1, okay, and this is true also for the old ones. Okay. So, each of these, the way we proceed is as follows. So, we know this from the orthogonality. What we do is that we take up each of these vectors and express them in terms of the old vectors, and then when we express them in terms of old and then do the dot, we see that we get an expression which involves the transformation matrix being multiplied twice, and then we will see whether the value is unity or 0. So, using the first expression, that is express x1 star in terms of x1, x2, x3, and then dot it with itself, then we will see that this expression, which is basically, if I want to expand it, T1 I T1 I is equal to 1 to 3 is equal to 1. Okay. So, this comes up because we are actually, what we are doing is T11 T11 plus T12 T12 plus T13 T13. So, this expression is going to be 1 because of the orthogonality of the new coordinate system, and this one I want to now imagine as if it were to be coming from two indices of a Kronecker delta, and I want to take those two indices to be what are here, okay, and we know the property of Kronecker delta. So, we just write it as 1. So, the reason why we write like this is because we see a very general form that is evolving here. When we take the orthogonality relationship with x1 star and x2 star, we get a 0. So, here again we choose those two indices here and realize that the expression is actually valid. So, we can then generalize saying that if the index is such that it is m and n, then we can write the expression using delta mn. Okay. So, whenever there is a summation of I, the other two indices can be used for the indices of Kronecker delta, and this is basically nothing but statement of orthogonality of the coordinate systems, both new and old. Okay. So, when we write the orthogonality of the new coordinate system expressed in terms of the old coordinate system, we get this expression where the second index is being used as dummy index. But if we do the reverse, that is we express the old coordinate system orthogonality and express the old coordinate system unit vectors in terms of the new ones, and do the same analysis, then we see that the dummy index is actually in the first position of T. So, we can see that either way we are getting the Kronecker delta on the right hand side. So, it is essentially what it implies is that whenever there are two T's coming up together, then inspect there are two indices, okay, and let us say if the first index is matching, then put the other two indices here. Okay. So, that is how you can write the expression using the subscript notation, and there is no deeper meaning in this expression than the orthogonality of the two coordinate systems. Okay. Now, there are some more properties of the transformation matrix that we can use. We can say that the transformation matrix is completely determined by the rotation of the coordinate system. So, whenever we know the rotations by what axis, by what amount, then we can then determine the elements of T completely. The determinant of T is 1. The reason why this is so is because we are talking about a pure rotation. We do not want to consider situations where the new unit vectors, when you look at the triple product, it is not different from 1. The unit cell is not expanding or contracting, the unit cell is of the same volume, we are only rotating the coordinate axis. So, because of that the determinant of T will be 1, and inverse is the same as its transpose. Okay, we have come across that already, and orthogonality leads to these two relationships. So, these are the four aspects of the transformation matrix to summarize what we have done till now. So, now we are going to use these to make some more analysis. So, why did we do all this? The whole idea is as follows. So, there are certain quantities which we want to represent irrespective of how the coordinate system is laid out. In other words, if you now take the example of a vector u. So, the vector u, if you look at its components, in the old coordinate system the components are u1 and u2, and in the new coordinate system the components are u1 star and u2 star. Now, if this vector u were to be, for example, a velocity vector or a gradient, etc., then we know that its sense of the magnitude and direction does not change whichever way we chose the coordinate axis to be. which means that when we rotate the coordinate system from x1 x2 to x1 star x2 star, then the elements u1 and u2 should change over to u1 star and u2 star and maintain the direction and magnitude of the vector. So, the sense of the vector should be preserved when we rotate the coordinate system, and only those quantities whose elements are following this sense being preserved will be actually called as vectors. Otherwise, it just becomes a bunch of numbers which change randomly when we change the coordinate system. So, this is the principle behind writing this expression, and let us just go through the small algebra that is behind. It is identical to what we have done with the unit vector. So, let us look at the elements. So, these are the two expressions we have taken. We have taken a 2D situation and we have taken this angle theta exactly like what we did in the previous exercise. So, to know how the elements u1, u2 are written in terms of u1 star and u2 star, what we do is as follows. We first write the u in terms of its components, and then what we do is that each of these unit vectors, which are old unit vectors, which we write in terms of the new ones, and we already have those new ones. So, this is the first one, okay, and this is the first one, and this is the second one, this is the second one, and the third one of course is unchanged because we are rotating about the x-ray axis. So, we have those expressions coming in. So, once we write the old coordinate system unit vectors in terms of the new ones, then we collate all the terms for x1 star, x2 star and x3 star, and then when we collate we get those things here. Okay. Then once we write, then we now have expression here u is equal to this way. Okay. Now, you can see that u1 star is now expressed in terms of u1 and u2, u2 star is expressed in terms of u1 and u2, u3 also is expressed in terms of u3. So, which we can then write in the form of a matrix. Okay. So, that is what we do here, and the way we are multiplying is the same as what we have done here. So, this is the way. Okay. So, u1 star is u1 cos theta plus u2 sin theta plus 0 into u3, u2 star is minus u1 sin theta plus u2 cos theta plus 0 into u3, u3 star is 0 into u1 plus 0 into u2 plus 1 into u3. So, we have got this expression, and it is actually not surprising that the matrix that is coming in here is nothing but the transformation matrix T. The reason is that we have actually used the unit vectors to arrive at this particular expression. So, the way unit vectors are transforming is given by the transformation matrix. So, we should get the same matrix here. So, we now have that expression here, and so the way the elements of a vector transform when the coordinate system is rotated is given by the same expression as we have done earlier, namely up star is equal to t pi ui. So, let us look at this expression carefully. So, for the new coordinate system indicated by the star, the index chosen is p, and then for the old coordinate system you do not have a star and the index chosen is I, and the sequence of writing the indices for t is the first one on the left, second one on the right. Okay. So, you should always remember that this is how it is written, okay, and the I is for the old, which is coming on the right hand side, and this way if you write, then when we swap the quantities, then the sense does not change. So, in fact, later on we will see that it is this expression that will be used to define what can be called as a vector at all. So, vector is one which transforms in such a way that the elements, the components of the vector will change in this manner whenever the coordinate system changes. So, we use that as a definition of vector. Okay. So, this is how we are defining here. So, we say that any bunch of 3 numbers cannot be a vector, only those bunches of 3 numbers which follow this relationship can be called as components of a vector, okay, and which can be proven. There are some quantities which are known to be vectors, so we can go ahead and prove whether they are vectors or not according to this relationship. We will be doing that in a later session. And are there any quantities that we already know are to be vectors? We have, for example, velocity. So, velocity vector is here, and we can look at gradient of temperature, gradient of composition, electric field and so on, polarization and so on. So, these are all various quantities that we know which are part of describing a physical process where the vectors are involved. Now, there is a small terminology I am introducing at this juncture, which is basically field. Okay. So, the idea of field is basically the quantity, the parameter we are talking about is having a particular value, at a particular location, but if you change the location the value could change. So, think of temperature field where the temperature at any given value given location is fixed, but as you change the location the temperature could change. So, such a quantity which changes as a function of the location is called a field. So, what we mean by a vector field is nothing but a vector that is a function of the location. So, velocity field, when we use the word velocity field, what we mean is this: a velocity which has 3 components, but those 3 components are functions of the location, and the location is specified in various means. Sometimes we specify the location using x, y, z, sometimes we specify the location using r theta z, sometimes we may specify using r theta phi in spherical coordinate system. So, the choice of the coordinate system is up to us, but once the location is specified and if the value of any vector is at that location specified, then it can be called as a field. And examples are examples of velocity fields, vector fields are such that you can see velocity field, gradient of a thermal field, gradient of composition field, electrical field. So, these are all things that we will come across in this subject again and again. So, the word field should immediately indicate to us that there is a location dependency that is coming up. Okay. So, now we have defined how the elements of a vector should change such that you can call it as a vector. So, we have given this. So, what would be then a scalar? Okay, scalar should be defined by a fact that the numbers do not change when the coordinate system is changed. So, basically we use the word invariant. So, a scalar is one which is invariant across a coordinate transformation. So, it does not change when the coordinate system has changed. Examples are of course temperature. So, we know that whichever way the x, y, z coordinate system is oriented, once we specify a location, the temperature of that location is fixed. It does not matter which way the x and y directions are pointing at. So, such quantities are called scalars, and very important to note that energies are all scalars. So, because later on when we define energies in terms of various quantities, we realize that because energy is a scalar, then whatever quantities we are using should be such that they must be having a functional form which does not change when the coordinate axes are rotated. The density is also one more example where it is a scalar field. So, now scalar field is something that we are introducing now. It is the same sense as what we have said for vector field. A scalar field is basically a scalar which changes its value as a function of the location, but not when the coordinate system is rotated. So, we have temperature field, we have density field, we have phase field, and so on. So, these are all various quantities that will be coming up as a part of this course later on. So, we will be using the word scalar field and in multiple ways, and whenever we indicate that, what we mean is that whenever the coordinate system changes, then the value does not change and the value is a function of the location. Okay. Now, the invariance is something that one can proven. So, that is, if there is a quantity which when we rotate the coordinate system has not changed at all for any transformation matrix T, okay, then for any TPI phi star and phi are the same, which means that phi is scalar. So, this is the idea that we are going to use later on to define what is a scalar and what is not. So, it is not as if any quantity which has just one number at a particular location can be called as a scalar. It is very important that that particular number should not change when the coordinate system is rotated by any arbitrary transformation matrix T. So, this is the essence of it. So, we will practice these with some assignments. So, we can go back to the course website and look at some practice assignments to practice with the coordinate rotations and arriving at various values of the elements of T, and then using the orthogonality arriving at various kind of derivations that we will be practicing, and look up the course website for further details.